Okay, now we're moving to the emerging investigators. So just as a reminder, one of the goals for ALD Connect was to engage the next, we have amazing, wonderful experts that right now we cannot allow any of them to retire. So we need to engage the next generation and encourage more research. So we started a program back in 2022 where medical students, grad students, postdocs would submit proposals and they would review with the panel of ALD experts and then present their work. So we're really pleased to have these emerging investigators present their work now. And we'll start with Yorick Jaspers, who is in the lab of Stefan Kamp and Mark Engelen in Amsterdam. And as we know, one of the challenges is that when you do get a diagnosis of ALD, we don't know which phenotype will develop. So this is really nice work to try to take a lipidomic approach to learn more in that regard.
All right, thank you for inviting me to speak here today, and thank you to ALD Connect for supporting our research with an ALD early investigator grant. So the project I'm going to talk about today is a follow-up to a recent publication where we show that, let's see if I can get a laser pointer here, where we show that lipidomic biomarkers in plasma correlate with the disease severity in ALD. Do you see my pointer or? Now you see it? Ah, great. So the setup of this study was as follows. We collected blood spot samples from male and female ALD patients and healthy controls. We performed high-resolution lipidomics on these samples, and then we had two goals. The first goal was to characterize the impact of ALD on the lipidome in general, and our second goal was to correlate the lipidome to disease severity. So when we compare ALD to controls, this is what it looks like. So this is a volcano plot showing significance on the y-axis and fold change on the x-axis, meaning that lipids in the top right here are significantly increased in ALD. And here on the right I show the lipid classes that are affected. And you can see it's quite a number of them. So taken together, this shows you that ALD really has a profound impact on the lipidome. Now, just for those who are less familiar with lipid nomenclature, here I show one example. This is PC 48.4. So PC, this stands for the lipid class or the lipid head group. 48 is the total length of the fatty acids that are present within the lipid. So in this case, this is a C26O fatty acid combined with a C22.4. So 26 plus 22 is 48. And the 4 here represents the total amount of double bonds that are present within the lipid. So when we consider the amount of lipids that change per lipid class, that is displayed in the plot right here, with lipid class on. Now we can take a closer look at these lipid classes. Here I show 3 examples. They contain a different amount of fatty acids. So the first one is LPC containing 1 fatty acid, PC containing 2 fatty acids, and triglycerides containing 3 fatty acids. Here the plots in the middle, the log fold change is plotted on the y-axis, and on the x-axis the chain length is shown for lipids that are present within each class, and the trend line here represents the difference between ALD and control. And what you can see is that there's a steep increase for lipids containing more than 22 carbons for the LPC lipid class, more than 42 carbons for the PC lipid class, and more than 58 carbons in the triglyceride lipid class. And this demonstrates that the increased lipids in ALD are the result of very long chain fatty acid accumulation. Another way of representing this data is shown here on the right. Here we plot the chain length of lipids in the lipid classes on the y-axis and the amount of double bonds on the x-axis. And the bubble size here increases with change when you compare ALD to controls. And as you can see, there's a steep increase of lipids in the top left corner of all plots, meaning that these are indeed very long chain fatty acid containing lipids. And the combination of these plots together is what I typically refer to as the ALD lipidomic signature. So I've shown you that ALD significantly affected the lipidome, characterized by this elevation of lipids containing very long-chain fatty acids. Our next goal was to correlate these changes to disease severity, and the first thing we looked at was, can we detect changes when we compare cerebral ALD patients versus patients without cerebral ALD? So in this volcano plot here on the top right, these are lipids that are significantly increased in patients with cerebral ALD. Here in the top left, these are lipids that are significantly reduced in cerebral ALD. Here I show 3 examples of what the data distribution looks like. So we define 3 groups here. In blue, patients without cerebral ALD of all ages. In green, patients without cerebral ALD over the age of 55. And in red, patients with cerebral ALD. Now we differentiate with age in patients without cerebral ALD because some patients in the blue group might still develop cerebral ALD at some point in the future. So their levels of these markers might already be elevated. And this is probably less likely for patients without cerebral ALD over the age of 55, as phenotypes tend to stabilize over time. Now, for 3 patients, we were able to collect samples before and after the onset of cerebral ALD, indicated by the yellow data points here. And what was interesting is that these patients already had relatively high levels of these markers even before the onset of cerebral ALD. Now we can also look at these groups and what their distribution is in the ALD lipodomic signature. And the same color code is here with red cerebral ALDs, blue patients without cerebral ALD of all ages, and in green patients without cerebral ALD over the age of 55. And what we can see is that the differences between these groups are specific for very long-chain fatty acid containing species, and that this difference is consistent for all very long-chain fatty acid variants that we were able to detect, and that this difference between groups grows larger as the chain length increases. Now, we found similar differences when we categorize patients based on the presence of adrenal insufficiency. So in red, patients with adrenal insufficiency, in blue, patients without adrenal insufficiency of all ages, and in green, over the age of 55. And as you can see, also adrenal insufficiency is associated with higher levels of these very long-chain fatty acid containing lipids. Also, when you categorize patients based on the severity of symptoms for spinal cord disease, we found that more severe patients tend to have higher levels of these lipids. We also characterized the lipidome of plasma samples from female ALD patients. Here also we were able to detect many elevated lipids containing very long-chain fatty acids. Also here we found a trend that more severe patients also tended to have higher levels of these lipids. And we were also able to correlate LPC-260 levels to X inactivation, showing a robust correlation. Now we had one female patient in our data set who had cerebral ALD. And interestingly, this patient had relatively high levels of our lipids that we identified, and it also had the most extreme level with regards to the X inactivation. So what I showed you is that we, based on our data, very long-chain fatty acid lipid levels correlate with disease severity in different ways. But of course, many questions still remain, like how do these lipid levels change over time? How do they react to different stimuli, such as infection or aging? And are these levels already elevated even before the onset of symptoms? So we need more samples, more measurements, and more data. However, the lipidomics pipeline, the analysis that we use for this paper, is quite challenging. There are multiple sources of complexity, and this is why it's relatively challenging to apply this at a large scale. So our goal for this emerging investigator grant was to make this platform more efficient and less complex so that we could apply it on a large scale. So the first challenge in this pipeline is plasma samples. So this is a challenge for international collaboration because these samples need to be shipped on dry ice. This often costs thousands of dollars in shipping. And it happened now a frequent a number of times that samples were actually lost in transit or that they were stuck in an airport. So to resolve this challenge, we switched from plasma samples to blood spot samples. So blood spot cards are an interesting sample type because they are less invasive compared to plasma samples. They require a small prick to capture a drop of whole blood on a blood spot card, and these cards can be shipped by regular mail and do not require dry ice. So the costs are far less. They're also easier to store, and they potentially also allow for remote sampling in non-clinical settings. So the LCMS analysis we used is also relatively complex. We use 4 measurements using 2 chemical separation modes and 2 ionization modes. So 4 measurements in total, and each measurement is a source of variability. And it also takes a long time, around 75 minutes per sample. And because we have 4 data files, the data analysis is also relatively complex because these data files need to be merged. So to resolve this challenge, we upgraded our mass spectrometer to a new Orbitrap Explorers 240. And using this new technology, we were able to optimize our lipid detection by leveraging the cluster formation that lipids demonstrate when you analyze them using mass spectrometry. And this basically allowed for the elimination of one of the separation modes we used. So we were able to cut the measurement amount from 4 to 2 measurements per sample. We also developed a new ionization mode. This new method is able to rapidly switch between positive and negative ionization modes. And this means that we can now, in one measurement, measure simultaneously positives. We don't have to merge this data. And it's also considerably faster, going from 75 minutes to around 21 minutes. So we then applied this new and improved blood spot lipidomics method to 100 ALD blood spot cards and 12 healthy controls. And again, we set out to characterize the impact of ALD on the lipidome and correlate the lipidome to disease severity. So this is a volcano plot comparing ALD versus control. And similar to plasma, we were able to detect many increased lipids and show that LPC, PC, and triglycerides are most affected. Looking at the ALD lipidomic signature, we were able to show that indeed these elevated lipids are the result of very long-chain fatty acid accumulation. So this basically means that the blood spot lipidomics method is able to capture this very typical ALD lipidomic signature. Now, when we compare the results from our blood spot platform to our plasma study, we see that for LPC lipids, the differences between ALD and control are very similar. And when we compare PC and triglycerides, we see that in blood spot lipidomics, we're still able to capture that very characteristic ALD pattern. However, when you look at the bubbles here, you can see that we were able to detect slightly less very long-chain fatty acid lipids compared to the plasma lipidomics. And this is likely due to the more complex sample matrix of blood spots, which uses whole blood compared to plasma. Now, what about the different disease forms? We were able to detect a significant amount of elevated lipids in cerebral ALD compared to patients without cerebral ALD. Same color coding here as before. And here I show 9 examples of significantly elevated lipids in cerebral ALD. And looking at the lipidomic signature, we were able to detect differences between these groups that were consistent for all very long-chain fatty acid containing species. And that indeed the changes in cerebral ALD are very long-chain fatty acid driven. And this trend is consistent for all lipids from this chain length. Interestingly, the triglyceride results were more variable. We were not able to find consistent differences between the group for this lipid class. And like I said before, this is likely due to the more complex sample matrix of whole blood versus plasma. Similarly, in adrenal insufficiency, we were able to detect a number of significantly elevated lipids that were the result of very long-chain fatty acid accumulation. And also here, triglycerides showed a more variable image. Now, one advantage of our new method is that it allows for untargeted analysis. So in untargeted analysis, every compound or every ion in the sample is measured if it goes over the detection threshold. So the data I showed before is based on the identification of around 1,600 lipids, but there are around over 30,000 unidentified compounds that are present within the sample. And using these compounds, we're able to make this lipodomic fingerprint. So this is one sample, positive ionization mode on the top, a negative ionization mode on the bottom. And each gray point here is a compound that is present in the sample. And this is useful for the identification of new lipids, but potentially also for the identification of new biomarkers. And our analytical pipeline is able to automatically annotate these compounds that show differing levels in different patient groups. For example, here in red, these are unknown compounds that we are not able to identify yet, but show significantly elevated levels in cerebral ALD. And in blue, these are compounds that are unidentified that are significantly reduced in cerebral ALD. So as you can see, there are quite a number of them, and a lot more data is needed to validate these findings and potentially identify what these unknown compounds actually are. But potentially down the road, this might lead to the identification of new or better biomarkers. Now with that, I arrive at my conclusions. I've shown you that our blood spot lipidomics platform is able to characterize the impact of ALD on the lipidome, that we were able to correlate very long-chain fatty acid lipid levels with cerebral ALD and adrenal insufficiency. It's considerably faster, going from 75 minutes to 21 minutes. However, plasma lipidomics did detect more very long-chain fatty acid-containing lipids for the PC and triglyceride lipid classes, but blood spots do offer significant logistical advantages, and this is potentially an important factor for efficient international collaboration. And with that, I want to thank everyone who participated in this research. I want to thank ALD Connect for supporting our research with an emerging investigator grant, and thank you for your attention.
Great talk, Yorick. So one thing that's been interesting in the genomics space has been the recognition over the past 5 to 10 years that a lot of the variants that we've identified in patients as we've gotten more data from different folks of different races and ethnicities and across the world, that suddenly we're much better to categorize like what's a variant that's pathogenic versus non-pathogenic. And so with the data that you're collecting, just like, is that something where you're also looking at race, ethnicities, or an opportunity to look at race, ethnicity, and see if there's any difference in where people are falling out with their different lipid levels?
Is yours not working?
I think it's working again. We haven't looked at that yet, but indeed this method is a potential tool to evaluate differences in different populations with regards to ethnicity, for sure. Yeah.
Any other question for York? Oh, wait.
I was just really interested that you mentioned a female with cerebral ALD, which of course we've always thought was very, very rare, and I'm sure there are other women in the room concerned about that. Could you perhaps tell us a little bit more?
Yeah,
if you know anything.
Yeah, I don't have any clinical information on this patient because I'm not a physician, but what I can say is that, if we go back to my slides, is that, yeah, that it's perhaps unsurprising that this patient had very extreme X inactivation skewing, and that this elevation in these very long-chain fatty acid lipids was consistent for all very long-chain fatty acid variants. But that's all I can say since I don't have further clinical information.
Okay. If no other questions, thank you, Yorick. Very good work.